Hello, everyone. Welcome to our webinar. Our topic today is sustainable structures built with engineered wood. My name is Karen Beebe, and I'm the Western Region Manager for APA's Field Services Division, and I'll serve as the moderator for today's session. APA is a nonprofit trade association representing manufacturers of a variety of common structural engineered wood products. In addition to quality verification and product testing, we conduct research to improve engineered wood products and systems where they are used. We also educate users and specifiers on the product's intended use and potential applications. Before we start today's webinar, I have a few housekeeping details to cover with you. We're bookending the discussion with our cameras on, but during the balance of the session, we'll have the cameras off to maximize the size of your slides. Our class today is approved for both AIA and ICC continuing education units, and a certificate will be provided for attendees to use for AIA, ICC, or other organizations that self-report continuing education. Your feedback is important to us. I would like to point out that a QR code has appeared on your screen. If you open the camera on your smartphone and point it at that code, a link will take you to the session survey. It takes only a few minutes to provide the feedback, but that's very important to the ongoing quality and continuation of webinars like this at APA. Please take a minute to conclude that, and we will also send you a link for our live attendees that you can fill out afterwards. Our presenter today is Roy Frederick, an engineered wood specialist for the Field Services Division of APA. Roy is an experienced home builder, having worked for 20 years in all aspects of residential construction, estimating, and design, including code compliance, design changes, and planned performance. He's worked for Brighton Homes, Trendmaker Homes, and most recently David Weekley Homes throughout the major markets of South Central and Southeast Texas, as well as Indianapolis, Denver, and Salt Lake City. Roy is based in New Braunfels, Texas, and is a graduate of Lamar University. For those of you just joining us, welcome to APA's webinar on the topic of sustainable design for wood frame structures. I will now turn the microphone over to our speaker, Roy Frederick.
Thank you, Karen, and welcome to everyone participating in this webinar. We're going to go ahead and get started now. On the screen, you're going to see a copy of the course descriptions you were provided upon registration. This course will give an overview of sustainability in the construction industry and what role engineered wood products have. This here is a list of learning objectives that we're going to cover during the course. We're going to discuss the importance of sustainability and how it affects our industry. We'll look at wood's overall role in sustainable construction. We'll learn the benefits of engineered wood products, and we're going to learn what you can implement in your practice today. Today's program is for the construction professional who is interested in sustainable construction but doesn't know where to begin. Our agenda will follow the learning objectives listed here. And first, we'll start by discussing sustainability globally, how buildings fit into this picture, how to compare different materials, and what makes EWPs sustainable. Also, we're going to cover the best practices you can implement today in your design and construction. So let's start by defining sustainability and what makes a sustainable structure. Sustainability, you hear, is a broad term tossed around a lot, especially now in the age of the conscientious consumer. The University of Alberta defines sustainability as meeting our own needs without compromising the ability of future generations to meet their own. If we consider the three pillars of sustainability as our environment, the society, and our economy, when we're not diligent, you can see that these pillars will fight for control. Our first step towards sustainability is to look at the intersection of these. Here, we will need acceptance, viability, and equity. And where those three coincide, we're going to find sustainability. When we don't treat our three pillars equally, we can face challenges. The first one we should discuss is the elephant in the room, and that's going to be climate change. It seems that we're going to see this every week on the news, This comes in the form of increased wildfires, severity of storms and droughts that last for years. These can be contributed all to climate change and the effect greenhouse gases have on the Earth. Our second challenge is population increase. The global population has grown from 1 billion in 1800 to 7.9 billion in 2020. This will only get worse as the UN projects the population to keep growing. Many estimates have total population at 8.6 billion by mid-2030, 9.8 billion by mid-2050, and in the year 2100, 11.2 billion. This will ensure that the strain on our natural resources will only increase. Now, why are all these points important? It's because both can lead to resource depletion. Every industry has concerns when we talk about resource depletion. Most notably, oil depletion. We see this at the pump every time we fill up. Every conflict, our social pillar, causes a spike in gas prices. Mineral depletion. Beginning with the Industrial Revolution, we have had a need for minerals and metals to supply our industries. This is our economic pillar. Deforestation. History has shown us that deforestation causes extinction, changes into climate conditions, and displacement of population. This can occur anywhere we have a drastic alteration of a habitat without any effort towards renewal. This is our environmental pillar. So, designing buildings to lessen environmental impacts has taken on greater importance. Now, how do we define a sustainable structure? Now, there are many definitions out there. Keeping the three pillars of sustainability in mind is, according to the EPA, green building is the practice of maximizing the efficiency with which buildings and their sites use resources, energy, water, materials, while minimizing building impacts on human health and the environment through the complete building life cycle, from siting, design, and construction to operation, renovation, and reuse. Now, later we will look at how engineered wood plays an important role in the efficient uses of resources, as well as how wood buildings benefit human health and minimize its impact on the environment. But first, let's take a look at how the guidelines, certification, and requirements for green building have evolved. Now, green building is nothing new to our industry. Starting in the late 80s and early 90s, this movement towards sustainable structures began. The next few slides show a timeline of just a few highlights. This is not intended to be an all-encompassing list, but it is important to see that we have been working at this for over 30 years. Here you will see we began in the late 80s when AIA created the Committee on the Environment. In the 90s, the EPA and DOE entered into the fray with the launch of Energy Star, along with the first local building program in Austin, Texas, the capital city of my home state. This was then followed by the U.S. Green Building Council's LEED program. Jumping to 2006, we saw a second green rating system, Living Building Challenge. This was followed in 2007 by the creation of the first green code in California, Cal Green. Lastly, ICC published a model green code, the International Green Construction Code, in 2009. Most recently, we've seen a shift in focus towards carbon accounting. Architecture 2030, the Carbon Leadership Forum, and SE 2050 all center on decreasing carbon emissions. Architecture 2030's mission is to rapidly transform the built environment from the major emitter of greenhouse gases to the central solution to the climate crisis. The action plan has two primary focuses. First, achieve a dramatic reduction in the energy consumption and CO2 emissions of the built environment by 2030, and a complete phase out of fossil fuel greenhouse gases by 2040. Second is to advance the development of sustainable resilient, equitable, and zero carbon building communities and cities. Carbon Leadership Forum's mission is to eliminate embodied carbon in buildings and infrastructure by inspiring innovation through collective action to create a just and thriving future. The SE 2050 mission is to work towards net zero embodied carbon structural systems by 2050 by transforming the practice of structural engineering in a way that is holistic, firm-wide, project-based, and data-driven. Currently, more than 90 firms have committed to SE 2050. These firms create an embodied carbon action plan to reduce embodied carbon by limiting global warming potential values and requiring product-specific environmental product declarations. This increasing the design features, biogenic construction materials, or designing for adaptive reuse and/or regenerative design. Additionally, in December of 2021, President Biden signed an executive order outlining the federal sustainability plan. The goal of this program is to achieve net zero emissions from overall federal operations by 2050. Additionally, major federal suppliers will be required to measure and disclose their greenhouse gas emissions and set science-based GHG reduction targets. So now, change in our industry will come in two forms. It's either going to be forced or voluntary. Forced change will come in the form of regulations, laws, and codes. Voluntary or elective change will allow you to choose the path to achieve the sustainability goal. From Architecture 2030, we learned that the building and construction sectors account for nearly 50% of global energy-related greenhouse gas emissions in constructing and operating buildings. Current building codes address operational energy, but do not typically address the impacts of embodied carbon in building materials or products. As building operations become more efficient, these embodied impacts related to producing building materials becomes increasingly significant. Voluntary sustainability programs might be geared to specific fields as such as, architects and engineers, but we will talk about specific programs in more detail later. These programs will often involve a commitment to reduce embodied carbon rather than just direct building emissions. Now, how do we compare materials that are so different? How can we take, say, apples and oranges and make them all apples? And even if we could do this, the goal isn't to find, one clear winner. The best materials for a building will be project dependent, but what tools can we use to compare products on a sustainability point of view? Thinking back to our EPA definition of green building, our goal is to maximize the efficient use of resources. In this case, building materials, while minimizing the impact on human health and the environment. The milestones of sustainable structure have shown the progress the industry has made. In the beginning, there was a heavy focus on energy efficiency in buildings. This is still important, but as buildings become more energy efficient, it creates an opportunity to shift the focus to the carbon emissions. And if this topic is new to you, there are several unfamiliar terms shared, and you can find out more information on this topic at www.apawood.org/acarbonexplainer. So now we're going to shift gears and we're going to go to a few definitions. Carbon accounting is the process of calculating overall greenhouse gas emissions associated with the chosen building materials. It estimates how much carbon is sequestered into materials versus how much greenhouse gases are emitted during material extraction and manufacture, construction, and eventually demolition and disposal, as well as the emissions during habitation of the building. These greenhouse gases are quantified as embodied carbon. They encompass all emissions that arise from the same phases as discussed in carbon accounting shown on this slide. And note that This global warming potential is reported in terms of kilograms of CO2 equivalent, but this number will include CO2, methane, nitrous oxide, and other heat-trapping gases. But do not confuse this with biogenic carbon, which we will discuss later. As noted, many sustainable goals have shifted from zero net energy buildings to zero carbon or carbon neutrality. This shift is occurring because more of our power production is coming from renewable resources. This production has jumped 42% between 2010 and 2020. The Energy Information Administration, EIA, anticipates another 2% increase this year. Additionally, California has hit short time spans of running 100% on renewable energy. So as we continue to transition to low or no carbon energy production, the embodied carbon becomes a larger global warming potential factor. Zero net energy refers to buildings that have no net power use during operations. Zero net energy buildings often have components that generate power and store it and or push it back onto the grid, compensating for the energy used during operation. Whereas carbon neutral describes a building that balances the amount of carbon emissions it generates with an equal amount of carbon sequestration. To obtain carbon neutrality, carbon is quantified in tons of emission versus tons of sequestration. If these are equally balanced, the project is carbon neutral, or perhaps even carbon negative if the tons of sequestration are greater than tons of emission. Carbon neutrality can be accomplished a number of ways, but often involves planting more trees, investing in reforestation projects, and other forms of carbon offset. Now, carbon offset is carbon absorption specifically intended to compensate for carbon emissions in the context of carbon neutrality. Offsets are often purchased as credits, on a 1 credit per ton sequestered basis. And these come from entities specializing in carbon offsetting. Operational energy is the energy required during the service life of a building, including lighting, heating, cooling, ventilation, and powering the building and its various systems. But operational carbon is the carbon emissions during the same activities. It does not include any repair or remodel activities. These fall within the category of embodied emissions of building materials. Carbon sequestration is the process of capturing, securing, and storing carbon dioxide from the atmosphere. The idea is to stabilize carbon in a solid and dissolved forms so that there doesn't cause the atmosphere to warm. Biogenic carbon centers on the ability of plants to absorb and sequester carbon. Plants and trees have a unique ability to remove carbon dioxide from the atmosphere and deposit that carbon into leaves, roots, and stems while oxygen is released back into the atmosphere. This carbon is released when the materials decay or they're destroyed. We should note that some materials contain absolutely no biogenic carbon. Others, like wood, contain considerable amounts. In 2006, the International Organization for Standards, ISO, under ISO 14025, set out to quantify environmental information on the life cycle of a product to enable comparison between products filling the same functions. This was the creation of the Environmental Product Declaration, or EDPs. These reports tell the life cycle story of a product in a single comprehensive report. The EPD provides information about a product's impact upon the environment, such as global warming potential, smog creation, ozone depletion, and water pollution. They are primarily intended to facilitate business-to-business transaction, although they may also be of benefit to consumers who are environmentally focused when choosing goods or services. The American Wood Council, AWC, has published several EDPs that cover cradle-to-gate carbon emissions for wood products. These values are industry average that cover the emissions from harvesting, transportation to the mill, and the manufacturing process. The EPDs for North American wood products account for biogenic carbon per ISO 21930, which requires either stable or increasing carbon stock on a national level, or that the forest it originates in is certified for sustainable practices by a third party. Again, all of these are based on industry average, not individual mills. Wood products typically result in far less emissions than their competitors for two reasons. First, wood products do not require drastic changes to the material's original form, unlike materials that need to be mined or refined. Second, wood manufacturers often use wood waste like bark and sawdust as fuel for powering the manufacturing process. This eliminates the use of fossil fuels, which have a much higher carbon footprint. After the product leaves the manufacturing facility, the embodied carbon calculation becomes much more project specific. One challenge can be calculating the transportation embodied carbon, as mills may not be located nearby the project in some parts of the United States. Many EPDs are cradle to gate, like the ones AWC publish. Some manufacturers will attempt to average the transportation distance, but not all. Carbon released during the construction phase should be included transportation to the site, running equipment on site. After the building is constructed, you need to evaluate the use stage. This is where we see operational carbon come into play. Operational carbon is more to do with how we power our buildings and make them habitable. Maintenance and repair is just like construction and gets included in the embodied carbon count. For this part, this period is flat, which we can see on this graph from CLF. Our last and possibly most interesting topic is end of life. A survey years ago looked at the average age of buildings demolished in the Twin City areas. Interestingly, the study showed no correlation between the materials of an age of a building being demolished. While most of our building materials can last a long time, most buildings are getting demolished before the end of their useful life. Therefore, I'm personally a big fan of adaptive reuse. Adaptive reuse projects reduce the need for demolition, but require the same amount of construction activity, whether that's retrofitting or refitting the interior for its new use. Today, Cal Green requires all projects that generate construction and demolition debris to recycle or reuse the debris at a minimum rate of 65%. San Francisco has stricter requirements, so you will need to check with your local jurisdiction. AWC and the Canadian Wood Council have partnered with Building Materials Reuse Association to develop an online North American directory outlining reuse and recycle operations for wood and wood products. Now, this is a breakdown of the construction and demolition debris generated during 2018 that has been pulled from an EPA report. Wood accounts for 39.5 million tons of debris that enter our C&D landfills. Now, these are different from municipal solid waste landfills. As a side note, this makes it look like we're knocking down all the concrete buildings, but this includes concrete from roads and bridges, which account for over half of that concrete slice. This graphic will look at wood product debris ended up in 2018. As you can see, only about a quarter is getting recycled. The remaining 73% enter landfills. Now, this illustrates our need to move away from a linear model of consumption, take, make, use, and dispose, Instead, we should probably adopt a more circular model in which we make, use, collect, transform, and reuse. Now, these can be achieved through long-lasting design, maintenance, repair, reuse, remanufacturing, redistributing, and recycling. Even as large amount of wood construction debris end up in landfills, this is still a form of carbon sequestration. A study done by the Australian Greenhouse Office showed wood debris buried for 46 years had retained 82% of their original carbon content. Here we're going to put all of these together. This is an overview of carbon accounting in the built environment. You've probably seen this graphic before. Our energy code has historically focused on operational carbon. Embodied carbon covers a much larger picture of what's going on. I added the module life cycle stages numbers reference since they referenced in multiple documents and presentations on this topic. Now, how does one calculate the carbon of a building? Is we can conduct a life cycle assessment, an LCA. An LCA is a comprehensive measure of the total environmental impact of an assembly or structure that examines its life cycle, start to finish. You need to have our bill of materials for the products, aspects of the buildings you wish to compare. Select an LCA software tool, and then there's a few of these listed here, and utilize environmental product declarations. While cradle to grave is ideal, some LCAs will end at construction, or as we discussed with the EPDs, will be cradle to gate. Now we're going to look at specifically at why wood is sustainable. You know, it seems every day we are learning more about the environmental benefits of using wood in construction and how it sequesters carbon in the structure over the course of its lifespan and allows for the replanting of trees to absorb more carbon. If this life cycle of planting, growing, harvesting to sequestering in buildings and replanting, that makes wood an excellent sustainable resource. You know, no matter where we live, forests play an important role in our lives. Healthy forests reduce greenhouse gases in the atmosphere by absorbing carbon dioxide from the air, thus combating climate change. Sequestered carbon is stored in trees, soils, the wood debris on the forest floor, and in long-lasting products made from harvested wood. The main takeaway from facts shown that forest growth has an annual net increase of 36% and attributes to a 15% carbon offset. Here are a few North American forest facts from the North American Forest Foundation. North America is the leader in certified forestry. Modern forestry standards ensure a continuous cycle of growing, harvesting, and replanting. Each year, the U.S. plants over 1 billion trees and Canada over 600 million trees. Both countries have spurred more than 50 consecutive years of net forest growth that exceeds annual forest harvest due to responsible forest management. Demand for forest products keeps forest as forest. Growth in demand for forest products has led to greater forest productivity and inventory for storing carbon. Just a 1% increase in annual demand for industrial wood products could drive 70,000 square miles of new sustainable managed working forest, and that's roughly half the area of the state of California. Global carbon dioxide could be reduced as much as 31% if builders used wood instead of concrete and steel. Now, zero net carbon, or AKA carbon neutrality, is a particularly hot topic in the market. Forests are natural carbon sinks. They take in carbon dioxide and give off oxygen. As the forest grows, carbon gets sequestered or stored into the wood. When the forest gets old and begins to decay, the carbon dioxide is released back into the atmosphere. By harvesting the timber instead, the sequestered carbon continues to be stored for decades to come. Now, despite the consistent use of wood over the years, we now have substantially more forest in the U.S. than we did 100 years ago. Now, if you're interested in digging into the details of this data, Katie Fernholz, who is with the Dovetail Partners and a board member of the American Forest Foundation, did a very interesting presentation on wood as sustainable material. You can find this presentation at the webinar section of apawood.org. The numbers she laid out were really surprising, so I'd highly recommend taking a look at this. Sustainably harvesting timber is crucial to the health of forest. Responsible logging helps in regeneration by freeing of space in the canopy. This gives greater access to the sunlight, water, and nutrients. It encourages new trees and other plants to seed in, take root, and grow. Additionally, selective harvests can be utilized to manipulate the overall composition of a stand. A wide variety of native tree species at multiple age classes can provide habitat for a wider variety of wildlife species. When the harvest is conducted sustainably and ethically, timber may be able to be harvested as often as every 10 to 15 years. This results in a continuous source of income as well as continual maintenance. And this benefits the overall health and productivity of the forest. Timber harvests that remove unhealthy trees can also thin out overstocked, dense forests that have become less productive because of increased competition for space, water, sunlight, and vital nutrients. The coarse woody debris that is left behind after harvest provides additional sources of food, cover, and shelter for wildlife, including a variety of insects, small mammals, reptiles, and amphibians. So here is a breakdown of the participation in forest certification programs in North America. These programs cover things like biodiversity and forest health. Forest certification programs verify the sustainable forest management practices of land management companies, forest product manufacturers, and other related organizations. This list provides a recent list of forest management certifications of APA members as found on our website. Now, we can recall the EPA definition for green building, which should minimize the negative impact on human health. Biophilic design does just that. Biophilic design is an approach to architecture that seeks to connect building occupants more closely to nature. Biophilic designed buildings incorporate things like natural light and ventilation, natural landscape features, and other elements for creating a more productive and healthier built environment for people. A growing body of research suggests that exposure to nature or its elements can result in an impressive list of beneficial effects, including but not limited to better learning rates, lower blood pressure, reduced stress, and faster healing. Now, this approach includes environmental features, natural shapes, increases in light and open space, and a closer relationship between human and nature. The inclusion of plants and use of natural materials such as wood products can reduce stress, improve comfort, enhance mood, and proper healing. The integration of abundant natural light in public space creates stimulating, dramatic areas that spur imagination, movement, and exploration. With architecture, the biophilic effect spans a broad range of elements that include positive personal response to daylighting, views of nature, use of patterns, and use of natural materials such as wood products. For additional information on this topic, there are 2 webinars available on our webpage specifically dedicated to wood as a sustainable building material. Additionally, Woodworks' carbon calculator is another tool you might find useful. It estimates the wood carbon footprint of your product. You input the volume of structural wood in the building, and the carbon calculator will estimate how much carbon is stored in the wood, greenhouse gas emissions avoided by not using steel or concrete, and the amount of time it takes the U.S. and Canada forests to grow that volume of wood. Now, next, we will move on to the benefits of engineered wood. With engineered wood, you'll be able to span further without trying to source impossibly large trees. When you order engineered wood, it will come cut to length, reducing on-site waste and transportation emissions. Engineered wood products are manufactured to meet certain strength standards and take advantage of a much wider range of species and grades. The process used to manufacture engineered wood is incredibly energy efficient, and thanks to advancing adhesive technologies, is continually improving the health and durability of our buildings. Engineered wood products are very predictable, both in dimension and performance. This is because they are designed and manufactured to maximize the natural strength and stiffness of the wood with durable, moisture-resistant adhesives and minimal shrinkage. Consistent dimensions are typically a big advantage for contractors because they don't need to make continual adjustments for warped pieces of sawn lumber. And this saves time and money. Column and beam products are produced in long sections of 48 feet or longer and can be custom cut to meet a nearly unlimited variety of applications. All of these products are manufactured to meet internationally recognized standards with consistent design values supported by continuous quality control with third-party oversights. On top of the dimensional stability, engineered wood is typically available in longer lengths. This results in fewer pieces to purchase and decreased design flexibility. Because we're disassembling the tree, removing some of the normal imperfections and reassembling, these products can outperform sawn lumber. I think the easiest place to see the benefit in this material efficiency is using the same loading and approximately the same size member, we can get a 10 to 20% longer span. Now, when we get these longer spans, the sawn lumber sizes become more unrealistic. And depending on your loading, the design also starts to become governed by deflection rather than strength. If we go on just bending strength alone, you might see increases in the order of maybe 30 to 50%. Long lengths and pre-cut framing packages also result in less waste, which impacts the amount of materials going into landfills. For the contractor, this could result in reduced disposal costs. When using conventional framing lumber, as much as 10% of the primary framing members are rejected due to excessive cupping, splitting, warping, and etc. Engineered wood can typically eliminate this waste because it is more dimensionally stable. One of the perhaps most surprising things about engineered wood manufacturing is the minimal use of fossil fuels. In fact, about 98% of mill residues generated in the U.S. are currently used as fuel or to produce fiber products. Now, this is according to the U.S. Energy Information Administration. Wood products and paper manufacture are the largest consumers of wood biomass fuel in the U.S. This fuel is replacing fossil fuels, which cost a lot more in carbon output. So even though wood products make up 47% of industrial raw materials manufactured in the U.S., they consume only 4% of the energy needed to manufacture. Now, the Bio-Preferred program's purpose is to spur economic development, create new jobs, and provide new markets for farm commodities. The increased development, purchase, and use of bio-based products reduces our nation's reliance on petroleum, increases the uses of renewable agricultural resources, and contributes to reducing adverse environmental and health impacts. The two major parts of this program are mandatory purchasing requirements for federal agencies and their contractors, and a voluntary labeling initiative for bio-based products. Wood structural panels, I-joists, glulam, CLTs, LVLs, and LSLs are all approved products for this program. The Carbon Leadership Forum published some baseline material data last year. I pulled out the wood products so you can see how they stack up against each other. You can see here there is a range for each product, with the lower end being the targeted gold and the green horizontal line here being the estimated median of concurrent production. As you might expect, combining two different engineered wood products can potentially give us the largest global warming potential among wood products. But if you check these median numbers, the majority of EWPs will fall below the 500 kilogram per cubic meter. Now, obviously, comparing the individual pieces isn't the whole picture. This graph shows the net carbon emissions of components below the dashed line and the assemblies above. When we change materials, our assemblies change. So while it's great to understand the baseline of individual pieces, comparing your typical assemblies will give you a better idea of the trade-offs. This summary is of existing framing bays recently shared by SE 2050. Each framing bay has specific parameters and is designed by 3 separate engineers. Each of those designs is then assessed by a life cycle analyst using 3 different programs. As more firms join SE 2050, there is an increased data collection on the different construction practices. Now, we can't talk about engineered wood without touching on adhesives. Starting in the 1980s, the U.S. began regulating formaldehyde in composite wood products. At that time, the common adhesive used in some interior products like particle board was shown to emit formaldehyde under high heat and humidity. In 2018, APA did some benchmark testing confirming that these more durable adhesives, the emissions were much lower. Testing led to the CARB exemption for APA wood structural panels, glulam, I-joist, and structural composite lumber. US GBC considers all 5 of these categories to be low-emitting materials, and EPA's Indoor Air Plus program prescriptively accepts all wood structural panels as meeting its indoor air quality goals. Comparing materials on a volumetric basis, we show why more is not better. Both steel and concrete use more energy, emit more greenhouse gases, and release more air and water pollutants during manufacturing than wood. Use of wood building materials can reduce the net carbon impact of a project in many ways, particularly because wood emits significantly less CO2 emissions from production than other materials. If carbon storage capabilities are factored in, the benefits of wood become even more significant. Now, even with all the tools available, sustainability can be difficult to quantify. The wood industry has taken its EPDs one step further by obtaining third-party verification from UL to certify the sustainable attributes of their products. If we apply the differences from the previous slide, we can compare wood frame walls to concrete and wood floor systems to steel. The carbon savings add up very quickly at 15 pounds per square foot for wood, or for the wall, and 22 pounds for the floor. So now we're going to move on to our last topic of the day. What best practices can you implement in the design and construction of your engineered wood buildings today. Now, these are just a few ideas and are intended to be a starting point. Let's look at some ways that less is more will help projects moving forward. Use light frame EWPs when you can. Use mass timber in EWPs instead of steel and concrete construction when light frame EWPs are not feasible. Use biophilic design, exposure structure, and utilize advanced framing techniques. Showing the benefit of using EWPs, APA's all-wood case study featured 2 buildings in California, one 4 stories over 1 and the other 2 over 1, that utilized a wood podium rather than a traditional concrete. Some of the benefits expressed were fewer trades on site, less mobilization time, fewer construction delays, improved framing efficiency, easier field modification, decreased mass for lateral design, smaller concrete foundation due to lighter buildings. The less materials used and the switch to embodied carbon superior materials equaled a sustainability win for both of these projects. The use of mass timber for taller buildings has had a large foothold in Europe and Canada for some time. The intersection of lower embodied energy and renewable resources propels the mass timber industry forward. As discussed, timber buildings store carbon in their structure for the life of the building. An 18-story mass timber building, for example, has a negative carbon imprint equal to taking 2,350 cars off the road per year. Now, this is according to C.D. Smith Construction Company, the contractor for Ascent. C.D. Smith spoke of the cost benefits by saying mass timber materials are not inexpensive. However, mass timber offers several cost-competitive advantages and long-term benefits. Columns, beams, and panels on average weigh 1/5 the weight of concrete and steel materials, this reducing shipping costs and requiring a smaller workforce to install. With prefabricated panels delivered directly to job sites, construction time can be reduced by approximately 25%, saving owners even more time and money. Furthermore, wood structures have a biophilic effect on people, increasing occupants' overall health and wellness, and give long-term value to the design. With the 2021 IBC code change, the U.S. now allows up to 18-story tall wood buildings. Another alternative is the substitution of CMU and concrete shaft walls with wood. We will again see the advantages and long-term benefits. Lightweight materials can reduce foundations, shipping, and labor costs, and streamline construction by reducing the number of trades on site for the superstructure. The Cathedral of Christ the Light in Oakland, California is a building that uses biophilic design in several facets: natural materials, natural light, and the use of patterns. And this enhances the new structure that was a replacement for the previous cathedral that was rendered unusable following a 1989 earthquake. The project leaders designed this new structure with resilience in mind and a design life of 300 years. Imagine the LCA and biogenic carbon that can be credited to this building. Real sustainability is not about a scorecard, and this was said by Dan Heinfield, architect of the Environmental Nature Center, a LEED Platinum certified building that he says, quote, wears its DNA. And it does this by displaying the structure rather than designing it behind additive materials. Now, although you're not awarded any points for minimizing drop ceilings or carpet, they chose to expose the wood, roof structure, and concrete slab and considered it an aesthetic asset as well as minimizing the carbon footprint. Advanced framing with 2x6 wood studs spaced 24-inch on center, combined with wood structural panel sheathing, is one of the most cost-effective solutions for builders trying to balance increasingly stringent energy codes with structural building requirements. These framing techniques optimize framing materials usage, reduce wood waste, and with effective insulating details, boost the building's energy efficiency. Now, there are several green building rating systems in the market. The three most common in the US are listed, and each rates relatively level or compliance or performance with specific environmental goals and requirements. Comparing these systems, one finds many similarities. Part of the reason is that LEED and green globes, they were evolved from the same source, the Building Research Establishment Environmental Assessment Method, or BREEAM. Both systems emphasize energy, water, and resource efficiency, site ecology, indoor and air quality, and pollution. LEED, or the Leadership in Energy and Environmental Design, is managed by the U.S. Green Building Council. This building system is completed by on-site or third-party verification. Many building types can apply for this certification program, including new construction, existing buildings, homes, and communities. LEED has 4 certification levels: certified, silver, gold, and platinum. Now, in 2016, USGBD added an alternative compliance path. With this, builders and architects allowed to gain a point by using certified wood from several certified forest programs. These forest certification standards are based on ASTM D7612-10. Green Globes is structured so that it can be done as a self-assessment in-house with a project manager and a design team. It uses a questionnaire that is aimed to help the user make changes to complete the certification. This process creates a roadmap for improving building performance and reducing climate impacts through the collaborative process supported by outstanding staff and expert assessors. Green Globes assessors are highly qualified individuals that interact directly with teams throughout the process, including visiting the property to review progress towards certification, providing feedback on opportunities for improvement, and collaborating with teams to ensure projects meet their sustainability goals. The Living Building Challenge consists of 7 performance categories, or petals: place, water, energy, health and happiness, materials, equity, and beauty. This program goes beyond the building itself and aspires to create a positive impact on the human and natural systems that interact with them. This slide shows the Bullet Center, which is a zero net energy and zero net water building. Though its design elements, occupants are encouraged the health and happiness petal to take the mass timber irresistible stairs and place petal bike to work. The building also serves the equity petal to advance the green building industry through ongoing community outreach, education, and public tours. Another resource are APA's green verification reports. These reports will help building officials and design professionals determine a product's eligibility for points under recognized green building standards. APA issues these reports to document the compliance of an engineer's wood product that is manufactured under a quality program audited by APA to specific international, national, or industry recognized green building standards. Now, finally, there are several programs that firms and individuals can join to further the sustainable structured movement. The Carbon Leadership Forum, Architecture 2030, and SE 2050 each have a mission to reduce carbon neutral buildings and want and need participants by the design and construction industry to make this goal attainable. Now, a few final sustainable structural examples to bring us to our conclusion. First, CLTs used in Washington State's Brailsford Visitor Center were manufactured from locally sourced wood that had been damaged by mountain pine beetles. This example of green recovery allowed the timbers that would have otherwise been discarded to be used and continue to sequester their carbon. If not harvested, these trees would have been left to fall over and decay. This would result in millions of board feet of kindling with the potential to become fuel for wildfires or decay, which ultimately releases their carbon back into the atmosphere, resulting in higher greenhouse gases. This study shows how Bethel School District took full advantage of wood's naturally insulating properties to improve energy efficiency of their schools. Increase in environmental and budgetary crunches have caused districts, architects, and builders to remain mindful of the need to build quality, durable schools while keeping them warm spaces that encourage learning instead of just an institution to house kids. According to Jim Henson, the Director of Construction and Planning for Bethel School District, the planned revisions from masonry walls to wood frame are estimated to have saved this project nearly $1.3 million. Now add the superior thermal properties of wood compared to concrete and steel, the savings to the school district will continue for years to come. Now, looking back at our Venn diagram discussed at the beginning of this presentation, the re-engineering of this Santa Barbara apartment complex using I-joist compatible glue lams, force transfer around openings instead of steel made this project more affordable, equitable, and the money saved was transferred to community amenities and environmentally friendly. Now that brings us back to our agenda. We define sustainability and discuss the measure and ways to change. We talked about how you can compare different types of materials by looking at their embodied carbon through their life cycle. We discussed the importance of responsible forestry and the various ways it helps the ecosystem. And it was demonstrated how the manufacture and specifications of engineered wood products make it the perfect choice for sustainable construction. And finally, we finished with concepts you can apply today to your project and enhance its structural sustainability. So now this concludes our program, and I'm going to turn the mic back over to our moderator, Karen, to see if we've received any questions.
Thank you, Roy. That was excellent. Before we begin the Q&A, and I know that we're right at time, so if you have to fall off, you're excused from class, so to speak, but the QR code has reappeared, so please take a moment if you haven't already, pull out the smartphone and get a snapshot of that QR code so you can go in and take our survey. Your feedback is important to us to help us improve our offerings moving forward. So with our last moment or so, I have a handful of questions, and we'll start with, where can we find EPDs for a specific product that is used?
Okay, EPDs we talked about earlier. You know, AWC will keep a list of product-specific EPDs that they have published on their website. You can also find manufacturer-specific EPDs by going to the individual manufacturer's website. And now remember, EPDs for North America wood products cover emissions from harvest through manufacturing and are not going to account for the transportation to the job site or any of the construction activities.
Right, yeah, it's kind of a good starting point, almost like a nutrition label for a product when you're thinking about the environmental aspects of it. And then a question about, I imagine a residential designer said, how do I apply this to residential construction?
Well, I guess there's a few ways you can do this. And first is use EWPs when possible. Try to incorporate biophilic design and leave some of these EWPs exposed, and this will help eliminate some of the additive materials. You can also look into advanced framing techniques that we've demonstrated. And there's also a couple of green building programs that are geared towards residential construction. What comes to mind is LEED for Homes, and the NAHB also has a standard, and these will give you a good starting point to go from.
Yeah, I think that's ICC 700. So thanks, Roy.
Yes,
one more question. We're working on a LEED Gold project. We're using panels, and we want to know if APA holds a Forest Stewardship Council or SSI certificate.
Well, APA is a nonprofit trade association, and we actually, represent the manufacturers. So we, as APA, do not, carry or do not directly hold any certifications. Now, we do have a list of our members on our website at www.apawood.org that do hold various certifications, and this can all be found on there if you just search under green building.
Thanks, Roy. And I still see questions coming in, which we will certainly get to. We'll share those with our field staff and allow them to get back in touch with you all individually. Before we conclude, though, a few more reminders. Make sure that you're signed up to receive our APA update newsletter so that you'll be notified of our future webinars and updates to our publications and standards. Our next webinar is October 27th on the topic of shear wall selection. So just a quick note on that. And how to receive the newsletter. To receive it, all you need to do from our homepage is to click on Sign In the upper right-hand corner. And then a drop-down menu will come down, and you'll select Register, and then let us know what you'd like to receive, in this case, the APA Update newsletter. APA has field staff located throughout the country. These talented people are available to assist design professionals, builders, and code officials. And their contact information is available on our website at apawood.org. Like Roy, located in New Braunfels, Texas, we have individuals located throughout the country and in Canada to be a free resource to all of you. And don't forget to download the AIA or ICC Certificate of Completion. And with that, I'd like to thank you all for attending. Have a great day.